All right, so this is the fourth class, the third of the lectures, and going to talk about a bit of review, a bit about parameterized types, and then we're going to go into laziness, which is by reputation what makes Haskell difficult, although it's really not that difficult, as one hopes establish. To give a sense of what's to come, lecture 4 is going to be more about laziness and some of the list functionality. List processing is important because even though you'll use other collection types often, it gives you a sense of what's out there, what the capabilities are. Lecture 5 is when we get into type classes, really get into depth about what they are and how they work. And then with 6, we finally get into monoid and functor type classes, or I'm sorry, not monoid, monad, the dreaded M word. And then on lecture 7, we're going to do more of that. That's all going to happen before I go on vacation. Lab 2 is going to be when I get back. That way, the week that I'm out, everyone can catch up, read the lab code, which will hopefully all be in a working state by then. It's pretty close. So yeah, and by that point, you should be able to read and write Haskell code at a reasonable professional level. So one thing I want to go over, you've probably seen this, anonymous functions using the backslash and the arrow. And it looks a lot like a lambda expression, and that's intentional. On the bottom, we have a 2-parameter anonymous function, just backslash x, y, arrow, the stuff, y plus x cubed in this case. And that works for any number of parameters. That is borrowed from the lambda calculus, where even though, as in Haskell and lambda calculus, every function, or they call it a lambda abstraction, takes one variable, we just allow the shorthand where we put all the variables together, treat it as a multi-arity function because conceptually it's the same thing. So, you'll often see lambda x, y, z rather than the nested single parameter lambdas. Nothing too exciting there, just worth going over if you haven't seen it. And now let's talk about the types. And you've probably realized by now that when you explore at GHCI, you get more general type signatures than what you may have expected. So you ask for the type of 17, you may have an int in your mind, but it says that's num a fat arrow a. It doesn't commit to a type. Or you ask for the type of this anonymous function x to x plus 17, num a fat arrow a. Well, it's most often something you encounter at GHCI because in source files you'll probably be specifying your types already. And if you want a refined type, you want a concrete type, as here, you'll be specifying it. And what exactly does it mean that 17 has this type of num a fat arrow a? I mean, that's something that seems a bit strange to us because it's not a defined type. And the thing to keep in mind is that the types live at the language level. If you think of a type as a set of values only, then that doesn't really make sense. But what it's saying is that looking at the literal 17, it can't commit to a type yet. It could be an int, it could be a double, it could be a byte, which is word 8 in Haskell. And the compiler is able to figure out that it lives in some type of the num type class based on the fact that it's a numeric literal, but it can't figure out which one. Okay, so let's look at the type for the identity function, defined as id x equals x. And we get a arrow a. So the question is, from that, how do we know that id5, where we've committed to int for 5, is well typed? And how do we know whether or not id, for one example, is well typed? So first I'm going to do id of 5, where we've already committed to an int. And the answer is that there's an implicit for all a before the AROA type of id. So what that's really saying is that id is, for any a that you can come up with, it's a member of a arrow a. So we can specialize it to int arrow int, because what the type inferencer is doing when it looks at id 5 and it knows that 5 is an int, is it's solving a system of equations. It's saying we have id, which is a arrow a for any a. We have 5 double colon int, which is an int. So that means a equals int. And as long as there is some solution to the system of equations, you're good. It's well typed.
Does it require only one solution, or could there be multiple solutions?
There can be multiple solutions, and that's where you get the type signatures that don't commit to concrete types.
Like num.
Exactly. That's when it'll say like num a, fat arrow, a arrow, a arrow,
Okay.
a. And that's fine. That's okay. It's just not as concrete as you often like things to be.
Mm-hmm.
But sometimes you want to write code that is, you want to write code to an interface, to a type class, without specifying which one. So that's sometimes what you want. So how about id? Is that well typed? We're applying the identity function to itself. Okay, so who thinks yes? Okay, so we have about, we have 4 people committing to yes. Who thinks it's not? So we have a lot of people who are not sure. I'm going to pick one of the yeses at random. Taylor, why do you think it's well typed?
Well, id of anything is well typed, right? So id of id is well typed.
That's actually reasonable. Yeah, yeah. I would go a little bit more into depth. I would say that the 2 instances of id, we treat them as separate because id has a generic type, and it doesn't have to have the same type everywhere that it appears in your program. So id2 is b arrow b and id1 is a arrow a, and we've renamed it because otherwise, that system of equations wouldn't work. We say when b is a arrow a, then we get the expression id2 is a arrow a, that quantity, arrow, a arrow a. So id2, id1 is a arrow a for whatever a you're looking at. What are you gonna ask?
So, I mean, like the ID or identification, in almost any language or mathematical is sort of like useless except in terms of an exercise. Like, do you actually use the int function in places?
Yes, you do. Because sometimes you have a function that requires a function, but you don't really want to do any work. So let me that requires a function, but you don't really want to do any work. So let me give an example. And the example I'm going to give okay, so actually, so the general folding for reducing is what's called foldmap. Don't worry about that type signature just now, but the way you use it is you pass it a function and then what you're mapping on, and it will perform the reduce. And it's able to figure out your reducing function with foldmap because you're mapping it into some monoid, and a monoid is the type that has a append or a combining operator already known to the compiler. So in this particular case, you just want to compile them together, so you'd pass in id. You're saying, I just want to use the identity function. So you do actually have cases where the identity function is useful. And
Does the, and this I guess is getting ahead of things, but does the identity function help with forcing laziness evaluation?
no,
That's what we, because in R, that's what you use identity for.
no, it doesn't force anything.
Okay.
It doesn't. I'll get into how to force evaluation actually later in this lecture. So type checking is solving a system of equations based on context clues. So who can tell me what the type of this guy is?
Is it string Boolean?
It involves, well, okay, so the Z is a char.
Oh, chars, yeah, not string.
So char
Char.
Boolean, how would you combine those types? Like, what's the right way to combine those types? Okay, so what's the union with left and right in it? Either. So either bool char, or is it either char bool?
Char. Bool.
Exactly. So it's either char bool is the type of that whole expression.
So it's a list of either char bools.
Exactly. Exactly. So that's exactly what it is. It figures out that it's a list of A because there's a list literal up there. Based on left Z, it says, okay, A equals either char X for some type X. Based on the part in green, right, false, it says A is either Y bool for some Y, and there's a solution to that system of equations, and it's able to figure it out. How about this? What's the type of this guy?
Same.
Okay, so you think it's the same. Does anyone else have a different opinion about it?
It's a list of the either, like a list of either types, but there's not. You can have separate instances, their own left.
But a list can only have one type in it.
Oh yeah. Okay.
Yeah, it's a type error.
Trick question.
Because it says A is either char X for some X based on the left Z. A is either bool Y for some Y based on the left false. And char is not equal to bool, so there's no solution to that system of equations. So it's a compile error.
And so if something is ill-typed, then the compiler will just not, like, that will be an error.
Exactly.
Compile.
Exactly. That's why static typing is great, is because the compiler will tell you before you even run your program whether there's an error. So you find your bugs quickly. Because one thing I've learned in software engineering is that the cost of a bug is an exponential function of the age of the bug. So if you can find it right away, rather than finding it in runtime, that's a really big win.
So then I didn't understand the previous example.
This one or the one before? This one's different because we have a right, a false. So the two type.
So left and right are different functions.
They're different
And that-
constructors into the either type, yeah.
Oh, into the either type. Okay, that's what I'm not familiar with.
The either type is the sort of generic way of saying this could either be an, either A, B is saying this could either be an A with a left constructor or a B with the right constructor.
Okay, so the fact that it was both less made it such that
It was
it arrived
expecting,
at a contradiction between char and bool, where in this case, there is not that contradiction.
exactly. In
Okay.
this case, the type clues don't constrain you into the null set, or they don't contradict.
So if you had more lefts in this list, they would all have to be left char.
Exactly. And if you had more rights, they'd all have to be right false. Okay, so what do you guys think the type of this first expression is?
Can you have an either type with the same type? Sorry.
Yes, you can. So you think it's either string string?
Oh. Yeah.
But it's a function.
Strings.
So, like,
It takes a boolean to either.
String string. That's exactly right. What do you guys think the type of this is?
A to tuple A.
Exactly. And what do you guys think this one is?
A to string.
Yep.
What was the first example, like, result in the string?
The first example has a left constructor taking a string. So we know that it's either string something. And then we have a right constructor on the other side. So we know that the other parameter of the either is a string.
Right. So if you have either string or string, why doesn't that simplify to string?
Because you still have left strings and right strings. You might want to preserve that distinction.
Okay.
You might want to say, okay, there are two, there's a left and a right string, but they mean different things. Granted, if that's the case, you usually would not use an either. You'd usually define your own data type and say, have something a little more descriptive.
Okay.
So you could replace this with fx, then I, else, here, and then it would become a bool to a string.
Exactly.
Okay.
Why do you need that either in this? Because
Yeah,
they're not going to
that's what
both
I was
occur at the same time, right? I mean, it's either if or else.
I mean, there's no good reason. It's,
Okay.
it's a toy example. Yeah, what's up?
So when you can create like on there in the wild a left eye, right? And
Yes.
then you can create like a right ear,
Mhm.
right? But like you could keep creating left whatever or right whatevers, right? Because they'd all have just an A as their corresponding other. So if you created these out in the wild, and then like I'm just wondering how it collates, because like in this instance it just assumes that you meant that like because you have to have type parity in this, it assumes that they are the left and right respective of each other because it has to return the
Right, because both branches of an if statement have to return in the same type.
so it collates those into the same either type for you.
Right,
Like it ties in those A.
exactly.
So then from then on out, after this statement, you can't use them independently.
Well, okay, so the result of that function is going to be either string string.
Yeah.
You could use left or right elsewhere in your program on different types.
So like say you bound, Z to left eye or Y to left eye, Z to right ear, and then you did this. Then you couldn't use Y as an either string something else anymore, right?
Yeah, that's correct. That's correct. That variable would have the more concrete type to it.
I have another question about that same line. So would it be ill-typed if we were to just take out the left and the right, since it's returning the same?
No, it would be well
That would be
typed.
valid. Okay.
It would be returning in the string type rather than the either string string.
And would it be okay to, like, maybe instead of I we had like an int there? Would that
Yes,
also work?
that would be fine.
Okay.
That would be fine. As long as you don't have lefts of different types, you're good.
Okay. Or if and else of different types, right?
Exactly.
Okay. Thank you.
Exactly. Lists and if then else and case expressions are three examples we've seen where everything has to unify to some type. So what's the type of the function up there?
num to num.
Okay, we have num to num.
Well, it's an A because you didn't specify a type, so it'd be an A to whatever.
A to num A.
It
Close.
depends on the definition of like the function or the plus function.
Well, you're conceptually right. It's just a matter of how you write it. It's num A, fat arrow, A arrow, A. The fat arrow separates constraints on the type, which are the type
Oh,
classes that it has to implement. So it's saying that for any A that's a num, that is a valid A arrow A. So what is the type of this next expression? Okay, so we have A arrow Boolean. Anyone disagree with that?
A has to be a list.
Exactly. Exactly. So it's list A arrow Boolean or arrow bool.
Doesn't that underscore match anything then?
It does,
Exactly.
but it still has to be in the same type as the empty list.
Oh, because the case statement would have been ahead of type error. If it was
Exactly.
That's
Exactly.
basically defining an empty function, right? Empty.
Yeah, that is empty.
Yeah.
So the last one.
they're a lengthable. Like a is long.
Actually, no, you bring up a good point. You bring up a really good point, which is that GHC 710 has defined the length function to apply to any traversable. So what I'm going to give you is not quite valid because there is actually a lengthable, not a lengthable, but a traversable. This is 7.8 type signature, but in 7.10 plus, you'd actually have a more general type signature. So don't worry about that. It's
So
not
length is predefined in this example as a function. Is that right?
Yeah, length is a function that you have. It comes in the what they call the prelude.
So there are things other than lists that are also traversables.
Yes.
I would
Yes.
think the string is.
String is a
string
list of characters,
Yeah.
but you can build like a tree structure and make it traversable. We'll get into traversable in lecture 7. It's kind of a big topic, but we will absolutely get into that. Okay, so which type signatures do you expect the code to compile on this definition of add 17?
Is that the only thing in the file?
Yeah, let's assume it's the only thing in the file. There are no other context clues. So A will compile.
Oh, is how many of them would?
Yeah, which ones?
All but C.
All but C. Does anyone disagree?
A and D.
We have A and D, we have all but C. Why do you think B won't compile?
Because 17 would have a type of, I don't know, I'm guessing that 17 might have a type of integer.
So 17 is a numeric literal, so it can be a double.
Okay.
So the answer is all but D.
What I do not understand what a double is. Sorry. I'm,
Double
like,
precision
looking-
floating point.
What does that mean?
So what that means is it gets a little bit into computer architecture, but basically there is a limit on the size of an integer, right, in terms of the number of bits that it can use. And that's like what runs through a processor. And then the architecture for handling floating point operations is completely separate.
So,
And then they're like, in a language like Ruby, that's completely abstracted away from you, right? But in other languages that actually have types well defined, they're not the same thing at an architecture level, so they're not the same thing at the language level.
so it's a terrible name. To get started, it's a terrible name. A single precision floating point uses one machine word in a time when 32 bits was the size of a machine word. Now, most modern computers, such as all these MacBooks, have 64-bit words. But at the time that it was coined, 32 bits was the norm. So a single precision floating point number had 32 bits. It used 1 bit for the sign. This isn't really that important. 1 bit for the sign, 8 bits for the magnitude, and 23 bits for the mantissa, which is the precision. And that wasn't enough to represent more than about 7 bits of accuracy. So there's double precision, which has 64 bits. I think 53 for the mantissa and 12 for, like, there's a trick that you get an additional one. I think it's 11 for the magnitude and then 1 for the sign.
So it's you would use a double when you need to be precise, like within.
In general, yeah.
Decimal points precise.
In general, so like
Thank you.
Yeah, I'll show this. So for example, pi in float it only gives you 7 digits of accuracy, whereas double you get a lot more.
Got it. Thank you very
That's a
much.
good example.
But yeah, it's an awful name. It's a legacy thing.
But usually int's going to be good enough, right?
Well,
So like,
Well,
do
anytime
need
you
to
have
do-
a fraction, right, you're not actually using an integer, because you're representing a rational amount, which relies on this architecture.
if you're doing
Magnitude and precision.
Basically, on our computer, 17 and 17.0 are 2 different numbers.
Yeah, yes.
they're represented very
That's why
differently.
in statically typed languages, you have to say, okay, this is an.
This is what I mean.
Your computers, it is an integer to use all this memory. Well, in Ruby, there are also objects. Yes, we are.
Like if you do 17 over 5, you're going to get a different number if you do 17 over 5. That's why you have to add a 0.0 to make division work the way you expect it to.
So I can think of double like a float.
Exactly.
Yeah.
It's a float.
It's like a super.
So another thing to recall is that the arrow type, the function type, is just a parameterized type. And A arrow B is just syntactic sugar for arrow of A and B using the infix notation. So the reason this is important is because syntactically, Haskell's types look like there are various exceptions. You know, you have the arrows, you have the tuples, but in fact, types are just essentially trees. You know, so arrow AB is how you would represent the function that takes A's to B's. But we give you the infix notation to make it cleaner and more intuitive. So the type level operator arrow is right associative. So that's what makes the currying work. You probably are never going to need to know this, but it's kind of cool. These are just some useful functions that if you don't know what they are, they're worth looking up. You have the arithmetic functions. You have quat and div, which are integer division. I think quat rounds toward 0 and div rounds toward lowest. Maybe it's the other way around. It's one of those things I just look it up when I use it. Mod, which is modular arithmetic, and then negate is the unary minus sign. For ordering, we have double equals is equality, and then slash equals is not equal, and then all the others are familiar. And then for logical operations, we have not, double ampersand is and, double bar or double pipe is or, and if you need to do arithmetical shifts, you know, that's the double chevron in C type languages. You have shift L and shift R in the data.bits module. As I said before, you know, don't fear the type class. Sometimes you'll see type signatures that look more general than what you need, but it entails all of those type signatures are entailed by num A, fat arrow, A arrow A, arrow A. One thing that's great that you get out of type classes is code reuse. Type classes are essentially the one thing that's good in object-oriented programming, which is the ability to program to an interface rather than an implementation. So here we write a sum function. We say the sum of the empty list is 0, and the sum of x cons x's is x plus the sum of the x's. By the way, don't write your own sum function because there's already one built in, and it's probably tail recursive, unlike this one, so therefore better. But you know, doing this, we get the sum function, and it'll work for whatever numeric type we want to throw at it, including a numeric type that we didn't even know existed when we wrote it.
So when you define sum twice, is that considered 2 overloads of the same function?
No, because we're defining it on different patterns. That's generally the idiomatic way of doing it in Haskell. Although I did screw one thing up. Let me fix this. Since it's not in the case of block, it should be equals on both. But yeah, that's you define the function for each pattern, and the compiler will be smart enough to figure out, okay, what he means is that I want one function called sum that behaves one way on one pattern and one way on another pattern. So conversions, kind of an annoying topic, but you need to know how to do them sometimes. When you want to take an int and promote it to a double, you use from integral. That will convert any integral type into any numeric type, hence the type signature that you see. All of the integer types are integral. You have int, which is your machine size int, integer, which is arbitrary size, word, which is like int, but it's unsigned, and then you have all your fixed size integers from 8 to 64. And this is how you would do int to double conversion. With double to integer, you have truncate, you have floor, you have ceiling, different rounding properties. I think truncate rounds towards 0, floor rounds lowest, and ceiling rounds highest. Real frac is a type class that you've probably never seen, but if you want to know what the instances of a type class are, you can use :info or just :I, and you'll get all of the instances that GHCI knows about. So it verifies that real frac is a double, and therefore you can use truncate to convert a double to an integer. Now, we have double arrow integer. Why do I not have double arrow int?
Because there's no guarantee that the size of your double will fit.
Exactly. You can do it if you want. You could. But in general, you should convert to an integer unless you know for sure that it's going to be a small number. Because int is, if you overflow the int, not only does it give you a bad result, but it happens silently, which I can demonstrate.
I
Fucking
think it's a
annoying.
lot of swear words, but you have to edit it out.
Oh, I don't edit out fucking swear words.
Why the fuck would you?
Exactly. So, for example, if you have this double and you truncate it to an integer, you get a reasonable result because that's the closest. Floating point isn't exact, and at a scale of 10 to the 100, you're already losing enough accuracy that but it's close within like 16 digits. If you convert it to an int, you get 0 because all the low bits are zeros because it's some huge floating point number. So yeah, and that's bad because it's a silent failure. You don't know that it's happening. All right.
Is it like a type class for int and integer?
Integral is the type class
Oh,
for
yeah, you said that.
all your integer types. So most Haskell programmers would say that the int type is legacy because its size is system dependent. And it's also boxed. So if you want performance, like really high performance, you're usually going to go for the unboxed integer or the unboxed int. If you want a fixed size integer, like say a 64-bit integer, you'll often use int64. So you do see int a lot for many functions, partly legacy reasons. And in my case, I use int a lot because it makes things fit on a slide. But if you have any concerns about size, you should just use integer because it's not that much slower. To convert things to a string, anything that's in the show type class will convert to a string. So ints, you wanna print it to the console. First, you have to convert to a string. Use show.
Is there a module or like some sort of extension that turns functions into instances of show?
Not to my knowledge.
Like, should you be able, is that metadata technically stored somewhere anyway?
Well, I don't know, because the nice thing about having a compiler, but also the dangerous thing from a metaprogramming perspective, is that your source code doesn't exist at
Maybe
runtime.
like just in GSC. You load it just in the GSC.
I don't think so. I don't know. I don't know.
Spoil source of a program.
I'm just spoiled.
So this is something that you'll see often. You want to find the type of some value that you know is a function. You want to find what it takes and what it returns, and you forget your :t, and you get this error. That's what it's saying, is that there's no show instance of that function. There's nothing wrong with the function value itself. The inverse of show is read, which will return into any type A that is a read type. So usually that's a case where you have to actually explicitly annotate a type. Because if you don't, if you just say read this string, it'll yell at you. So for example, there, it tries to guess what it's reading, and it says there's no parse. I don't know what type it's reading in. But if you say, okay, I want to read an int, it'll figure it out. And if you say, oh, I want a double, it'll do the right thing. So that's a case where you do need an explicit type signature.
Is there a read maybe?
There is, and that's the next thing I was going to get to, is there's read may in the safe module. There's also read def, which allows you to give a default value. Say, okay, read this string, and if it doesn't parse correctly, then use this other value. So that's exactly what you should do. Non-IO code should not be throwing exceptions as a general principle. So recursion. What is recursion? It's recursion. It's preferred over looping in general. So on the left, we have the C-style factorial, which, by the way, is how you'd actually write factorial in most languages, because using recursion for factorial, while it's a good demonstration, it's not how it's actually done. On the right, we have three different ways of writing Haskell factorial. The first is a naive recursive factorial. The middle is tail recursive. So by threading in this accumulator, you don't have, you have the tail, you have what's called tail call optimization available, because it either exits returning the accumulator, that's the then clause, or it goes to the else clause, where it's another call to the loop function. It's able to say, well, I don't have any enclosing context around this loop function, so it can throw away the enclosing context from the factorial function and just do another iteration of the loop. So that way you avoid your stack blow up.
So it reuses the stack frame.
Exactly. Exactly. And then on the bottom, we have what I would do, because it's like, fuck it, I'm going to be lazy. And that's probably the most performant way in any case.
So that middle one actually not go back through all the function frames, just return together.
Well, it's gonna throw away the old function frames, because
Once it gets to the end, it'll know to not bubble all the way back up. It'll short circuit, right?
So it's gonna know that as it goes down. Now it may have what's called a thunk leak, which I'll get to later in this class, but it's gonna say, okay, let's say we're doing factorial 5. So it's gonna be loop 1, 5, and then it goes to the else branch and it says, okay, I multiply the accumulator by 5 and I decrement n. So that's loop 5, 1, loop loop 5, 4. The next iteration it goes to loop. It's just another call to loop. So then it says loop 23, loop
It doesn't get
62.
to the bottom. Like when you're visualizing the stack frames, it doesn't ever create a bunch and then short circuit on the way back up. It doesn't create more going down.
The compiler's smart enough.
It stays at its own stack frame.
Yeah, the compiler's smart enough to turn it into an iterative program. Because when we talk about state, and how it's bad, we really mean it's bad in source code, because the machine itself is stateful, and that's okay because the machine knows what it's doing. It's with, you know, limited creatures like humans who don't have all that RAM that state becomes a problem. So sequencing effectful computations. Sometimes you do actually use looping, but I'm going to show the general sequence function. We went over I/O in the lab. It's just an action that returns an A. And sometimes you have a list of actions, and you want to condense them into a single action that returns a list. So this is the sequence the sequence function. It just does all of the actions, and then it returns the list of the results. And so an example, we have this get file size function. You give it a file name, it does some I/O, it returns an int, which is the file size. And if we create this list of actions, get file size lab1, get file size lab2, get file size of the README, and we call sequence on it, we get an I/O list of ints. And one thing that's not clear from the GHCI session is that these returns are actually up top where it's 7038. That's an I/O event, but GHCI will just say, okay, I'm going to print the int, because GHCI is already doing I/O anyway.
Is that like file size function actually like, is that in some library?
Well, I wrote it
Oh,
on the left.
I thought that was just the.
I wrote it using system POSIX files. So an exercise for the weekend is to write sequence. I'll give the answer next class. Instead of taking a regular function, A arrow B, it takes A arrow IOB and a list of A's, and it returns an IO of a list of B's. So it's a map that can have side effects, and the result is that it's going to do all the side effects left to right, and then it's going to return the list of the values. We have mapm underscore, which is the same concept, but it throws that list of returns away. So that's when you're just doing an iteration and you don't care about the return value. You're just doing it for side effects. We also have form and form underscore, which give you a for loopy syntax because the arguments are flipped around. That's the only change. Recall that flip is the function that takes a binary function and returns the same function with the argument order swapped. So these are three ways of saying the same thing. One, we're creating the I/O actions, the I/O events explicitly and using sequence on them. The second one, we're mapming get file size on a pure list of strings. And then the third one is the same thing, but with form.
So it's an IO list.
Exactly. Exactly. It's an I/O that returns a list of A's, or a list of ints.
Oh, so the whole, the IO is wrapping the whole array, not an individual.
Exactly. So you only have a single I/O action to think about. Because your program itself, your main function is always an I/O of unit. So your main function is always a single I/O. Now sometimes if you have a list of I/Os, you want to condense them into a single I/O, you use sequence. Sometimes you also have an I/O of I/Os, and you can condense that using join, which I'll get into later. You can always condense your nested I/Os to a single I/O. What you can't do unless you're breaking the rules is take something in an I/O and turn it into something that's not I/O, because that would be defeating the whole purpose of all of this stuff.
Wouldn't it be sane though to be able to make like the same way you can unwrap pretty much anything that's inside of a runner? So make a check like to look at what's there and say like, okay, this is good, take it out.
But you should only be looking at it inside the I/O monad, because a pure value means it's referentially transparent. It means that it's always going to have the same value. So something like get file size, even though that doesn't have any stateful effects, it still depends on the state of the file system.
But once it's done, the result is the result.
But that number might change if someone changes the file. And the compiler, if it sees an int, the compiler knows it only has to compute it once. If it sees an IO event, it says, okay, that value is dependent on the state of the system, so I may have to compute it multiple times, so I can't.
So if you said let x equal get file size and gave it a file name, every time you ask for x, it's going to compute the file size of the thing?
Exactly, because it might change.
Oh.
Yeah, unless you want to set up a caching layer, which, I mean, you can set up a caching layer for I/O, you know, because there are mutable data structures in Haskell, and we'll probably get to them in the second half of the course. So here's a looping construct using form underscore, you know, and it looks exactly like a for loop. You say for 1 to 5, print I. You know, we're actually passing it a function, which is lambda I arrow print I. And on the right, we have a sequence map construction, which is printing the squares and then returning the squares. So now let's change topic to laziness, as Omar, as you can see, is fond of.
Is that the view from your apartment?
It is, yeah. And that's
Can
my
we determine your address given just that information?
maybe.
If you were good enough at Haskell, you probably.
Wait a second. Is that simply agreeing from the kitchen?
No. So you guys have probably heard that Haskell's laziness makes it hard to reason about code, but I would say that that concern is overblown because, yes, it's true that errors can happen on unexpected times with laziness, which is one of the reasons why I don't like error exceptions in non-IO code. And secondly, laziness can make it hard to reason about performance. But laziness is opt-out. It's not mandatory. You can write strict Haskell code. That's something that we're going to see later on. And high-performance Haskell often is strict. So the laziness is the default, but it's not always the case. But there are advantages of laziness. You avoid unnecessary work. That's a good thing. You can have infinite collections. You obviously can't hold the whole thing in memory, but you can represent them in your code. And finally, there's no distinction between your control flow operations and your regular functions, which I'll show what I mean in a little bit. So with infinite collections, this isn't a very efficient piece of code, but it works. And I would like to believe that it's fairly elegant. On the left, we have taxicab, which is an integer to bool function. The first thing that we do is we compute the integer cube root, meaning the smallest integer whose cube is less than or equal to it. We do that using take while, which I haven't gone over, but it will basically take from a list until the condition is false. And then passing that into last, we get the largest integer whose cube is less than or equal to n. And then the second thing we do is at the bottom left, list comprehension, where we say, okay, I want x to range over 1 to m, y to range over 1 to m. We set a condition that x is less than or equal to y, because we want to get rid of our duplicates. And then another condition that x cubed plus y cubed is equal to n. And if that list of solutions is greater than 2, greater than or equal to 2 in length, then we have a taxicab number. And on the right, again, we have an infinite collection. That's what the 1 dot dot is. That's all the integers starting from 1. We filter taxicab on that. We still have an integer collection, or an infinite collection. But then we say, I want to take the first 5 elements. And it's smart enough to run down the list. Once it has 5 elements, it stops. It says, here are your 5 elements. And you know, I'm done. I'm not going to compute that whole thing. So thunks are a key concept. It's kind of like a promise. It's a piece of code that has not been evaluated yet. Now, in strict by default languages, you often build your thunks with 0 argument functions. Or in OCaml, you actually don't have a 0 argument function, so you have just a one argument regular function that takes a unit, which is a nothing type, no information. So on the left, we see how it's done in Clojure. You create this thunk at the bottom, thunk7. It's a 0 argument function that when it's called will compute 3 plus 4. And then you force the thunk by calling it with no arguments. In OCaml, we create the same thing. It's a function that ignores its argument when it's called, but adds 3 to 4. And the way you force the thunk is you pass it a unit. But in Haskell, an A is a thunk by default. So this thunk7 doesn't add 3 to 4 until we need it. And that's what makes these infinite data structures possible. So here's an example where we're taking 2 from the list of all positive integers. The semantics of take are up top. If it sees a 0, it returns an empty list. If it sees an n that's not 0, because remember the pattern matching is from the top to the bottom. So take n empty list implicitly means for it to even hit that pattern, n is not 0. Take anything from the empty list, well, it's just the empty list because there's nothing more to take. In the case where you have a non-zero number, I'm not handling negatives properly, but just assume that that's positive, and a cons, then it says, okay, I'm going to take the x and cons it onto take n minus 1 of the rest of the list, the x's. Now these curly brackets, that's not Haskell syntax. That's something I'm using to say a thunk with this in it. So whatever's in it hasn't been evaluated yet. But when we take 2 from this infinite list, well, the first thing it does is it pattern matches. It says, well, okay, n is not 0, it's 2. It's not an empty list. Well, it has to figure out whether that list is an empty list or a cons. And it's like, it's a cons of 1 and this other list that starts at 2. So it's 1 cons, take 1 of the infinite list starting at 2. And then because 1 is not 0, again, it has to pattern match on the list, figure out if it's dealing with the empty list or a cons. It says it sees that it's a cons, so pulls out the 2. Now we have 1 cons, 2 cons, take 0 of the infinite list that starts with 3. Well, take 0 of anything is the empty list. So we have 1 cons, 2 cons empty list, which is exactly 1, 2. So that list starting from the 3, that's never evaluated. The thunk is there. Haskell knows about it. If it needs it, it can evaluate more. But since it only needs 2 values, the remaining part is never evaluated. You also get short-circuiting logical operators for free. Now, in many languages, you can't define your short-circuiting logical operators as functions. Does everyone know what a short-circuiting logic operator is?
It doesn't evaluate one of the 2 if it gets to one that already satisfies the condition of the one.
Exactly. Exactly.
False and
Right. Or a more common case is if x is not null and do something with x that would blow up the world if x were null. So in this particular case, we're trying to define and as a function. And while it gets the correct result, it does too much work. But in Haskell, and is defined this way. If it sees a true and a b, then it knows, OK, I have to evaluate that b to figure out the value. But if it's false in something, it just says, oh, that's false. And it never evaluates the second argument.
Does this mean you can also, like, you define like another operator can be flip of this guy? It would do the same thing but right to left?
Yeah, you could. You could. You could have a. Yeah, I believe that's right. Well, let's actually figure that out just to establish it as true rather than guessing. So, I mean, to demonstrate that this is just going to return false, and then if we do flip, No, that's what we expected.
Yeah.
But
That's okay.
there we go.
Oh, nice. Yep, and then
So that's how you reverse the order. So yeah, here's an example of what goes on. It starts with a thunk that says false and error barf. It evaluates that. It says, okay, it's an and of these two things. It has to evaluate the first thunk because for the pattern match. So now it's and false and this thunk that throws an error. And because that matches the second pattern and returns the value false, we never have to evaluate it. We can throw it away.
Doesn't the false have to go first, or does it just stop as soon as the thing doesn't meet the pattern? Like it doesn't evaluate B because because true doesn't meet the pattern.
Yeah, so the pattern match doesn't evaluate all of the pattern match will evaluate the constructor, will evaluate to the constructor level.
Okay.
True and false are two constructors in the bool type. You can think of like, say, int as a value as a union of like 2 to the 64 constructors if you want. But it won't evaluate more of the pattern than it needs to.
Okay. So as soon as it sees the first thing is false, it doesn't look.
Exactly.
So can you go back?
Sure.
How does it know if instead of like asking false, you had like some complicated computation that ends up in false? How does it still know to do the
It would do the
pattern matching the correct word?
It would do the complicated computation. It would get a false, and then it would pattern match. It knows to work left to right in this case. In fact, its tendency is going to be to work left to right because of the currying. Although, as we've seen, you can make it not go left to right with the flip. But yeah, it's going to do the complicated computation first because in this particular case, it knows that the first argument has to be evaluated. So what do you guys think that the answer to this is going to be?
Is it just going to be function signature?
No, it's not asking for a type.
Oh, okay.
Oh, definition of length never actually references the stuff that's inside.
Mm-hmm. That's correct. So the answer is, anyone?
2.
Yeah, exactly.
What?
Because length is just interested in the structure of the list. It doesn't have to look at what's in it. So here's the thunk evaluation pattern. And as you can see, yeah, that thunk 1 quad 0, that's there, but it never gets evaluated in calculating the list. Now here's the part that's dangerous. You can have thunk leaks. That's a profiler's graph of a memory leak. So before I get into thunk leaks, let's talk about folds. Folds are a very useful family of functions. They represent reduces. And Foldl folds from the left. So we have the definition in the middle, and at the bottom we have sort of mathematical representation. You give Foldl a function, which is your combining function, an initial value, and then the list. And it's going to left associate. That's wrong. That's completely wrong. Let me fix that. It's left associative. That's where I'm wrong. It folds from the left. So my apologies. Now it's correct. So it's left associative fold. it combines x0 and x1, then it combines that value with x2, and so on to the end. And this is how we would define it if it wasn't already defined. We define it recursively.
What do you have to do to the n minus 1 and then to the n?
Oh, it's just a formatting thing.
It just
explaining.
Yeah.
should be underscore, should be subscript.
Yeah, it could be subscripts. I mean, because it's supposed to look like code and you don't really have underscores or subscripts in Haskell code. That's the idiomatic way of writing it.
And is the last number. Make it an underscore is one is that.
Or are you
Yeah.
just saying that that could be the function applied all the way through x to the n?
Yeah,
Is that what
it
you're saying?
applies fn times.
Sorry, I thought that was like actual syntax. I thought that was like the syntactical.
Oh no, that
Do it.
bottom line is just mathematical representation.
Okay.
I mean,
Sorry.
you could have that syntax, except the dots, the ellipsis would have to be, actual content.
They have arbitrary Unicode names in Haskell for the-
You, pretty close.
like R, you can just close the name.
Yeah, I mean, you can't start with a letter, or I think you have to start with a letter. You can't start with like a number, so you couldn't have like 3x, but I think it's pretty close.
Confirmed.
So here's what a foldl looks like, this time written correctly. We're folding from the left. Our initial value is 867, and then we add on everything in the list going left to right. And at the bottom, we have the fold R. Fold R starts from the right. So it's right associative, and you put your initial value at the end of the list. So in this case, we have a red dragon draws near, and our initial value is the bang, and it right associates with the initial value at the right of the list.
So that doesn't matter for these because they operate the same right and left associated.
Well, oh yeah. Yeah, these cases are both, they both associate the same way, so the only
If you did
difference you
subtraction,
get.
it would be important to have the two.
Right, for subtraction, the difference matters. And the other thing is where the initial value starts, because if you did a fold L, then your exclamation point would be at the beginning of the final list.
Yeah. Oh.
So here's a quiz. What do you guys think this value is?
Actually, calculating.
I'm sorry?
Actually,
Yeah,
Well,
That
you-
requires sum of 1 through 5.
Yeah, that requires math.
Exactly.
I got as far as 5 plus 4, and then I got bored.
About like 20.
You guys are true mathematicians.
Way to
It's-
make us feel dumb, buddy.
It's the sum for Mike.
Exactly. It's 15. If you said it sums the
Oh,
number,
so it just drops the 2 dot dots out. So the next one's 14.
That's how we do it. That's how we do it for everything, right?
I think so.
All right, so what do you guys think this is? And you don't have to compute it if you don't want.
Will it be 10, right?
24.
Or
No, it's
times three.
product, that's not it.
Oh, product. Okay.
24, that's correct. What do you guys think this is going to be?
Zebra, bear, apple.
Apple,
Peter,
bear,
you're right.
zebra.
Apple, bear, zebra.
First digit is just 10 plus.
Yeah.
It's full right.
What do you think?
I think zebra, bear, apple.
Okay,
Fold right.
it's fold right.
So fold right actually means, wait a minute.
Wait
If you put
What?
because the accumulator goes on the left.
Yeah, because you have 10.
Yeah.
This-
Aha.
Anything plus
yeah.
plus.
Oh,
Yeah,
alright.
so it's
Yep.
being drawn from the.
I was so certain. Alright.
Is anyone confused about that at this point?
It always goes
I like the way you just
order.
said it actually. The accumulator goes on the left.
Yeah.
I like that.
Well, no, the accumulator
Goes on the right.
in fold R
Or
goes on the
Is
right.
that right? Well,
Yeah.
Darn.
Yeah,
No. So the way I conceived it when you said it, right, was that
Yeah.
the list, right?
Yeah,
You take the last
basically
element
we're
from the
thinking-
list and
Yeah,
you
yeah,
just
yeah.
stick it to the left side
Exactly.
of
Yeah.
your first element.
Oh, I get it.
Yeah. That's
That's
what
what I
That's what I
conceptualized
meant.
when you
That's-
said.
that's-
That's what you meant, right?
You
Yeah,
append
yeah.
to the left.
So
Yeah,
from the right.
Why is bear appended to the right side of zebra rather than the left side?
No, zebra
No,
is the
bear
initial
is
value,
dependent to the-
Is it to the left and then apple's dependent to the left
and then
again?
bear is left dependent to it, and then apple is left dependent to
So-
that.
Yeah,
So it's not that
zebra-
bear is right dependent to apple, it's that bear is left dependent to zebra and apple is left dependent to bear.
Is one way of thinking about
Okay,
it.
I see.
Well, he got it, so.
If you write it out with the parentheses, you'll.
So what do you guys think this is?
Or just take two numbers.
3 zeros.
Ooh, hold on a minute.
Uh,
This is a.
so it takes X, Y, it drops
For the-
Y.
for the
No one
people
likes Y.
Really paying attention.
The arrow.
So it's gonna take a
Oh.
3
Yeah.
0 and drop.
Hold on.
That's
No,
not a
hold on.
map.
What? Is that an error?
No, it's not
No,
narrow.
it's a reduced.
It's valid.
So like it starts with
Oh, okay.
it starts with 0
So
and
it's gonna be
3,
one.
and then
Yeah,
One, yeah.
it is one.
Does anyone disagree with one?
I like 1.
I like that. Small.
What is that?
Oh, 0.
Why do you think it's 0?
No, it's not narrow.
Because
It's like
it's a
two
function that
arguments,
takes an
X and
argument.
Y, and the body of
So
the
what's-
Function takes two arguments.
So
function takes
two
two
arguments.
arguments.
X,
Oh,
X
X.
is 3 and Y is 0 in the first one.
Oh, yeah.
Okay, so it takes,
It takes two arguments. So the first two arguments
thinking
is
the same
you got
thing.
3.
One.
and then just
Right.
returns the first
And
one.
the
one.
Y
Zero.
comes.
Yeah.
And it returns the first one, which is 3.
Then it
And then
does
it
that with
takes-
2 and 3.
How
2
do you
and
know
3
that?
and returns 2. And then it takes 1 and 2 and returns 1.
Because that function's always going to favor the left argument and throw the right one away. So even though it starts with a 0, that 0 is thrown away in favor of a 3. Then that 3 is thrown away in favor of a 2. Then that 2 is thrown away in favor of a 1.
That's how Haskell implements first.
This might be a dumb question, but how do you
Good
know,
job.
how do you know which one starts as X and Y in this example right now? This is what I'm
So-
confused about.
On a fold L,
It takes a
Yeah.
function that takes two
Well,
arguments.
yeah. Well,
And
so
it applies
zero
them
is technically-
specifically in the left one, in the first
Right.
argument, and
So-
the second.
Right, but which one, how do you
It's like
know
the
that 3
value
is the first argument,
at the
3 is
end
X
of the
instead of
list.
0?
On the
Okay.
definition of fold R.
Yeah.
Such that that's how the line is.
fold R puts the accumulator on the right
Well, if
because
there's only one
it's
element of
associating
it,
from the right.
Okay,
Fold
Yeah.
L puts the accumulator on the left.
so if it were to be a fold L, then 3 would be taken.
If it was fold L, it
Or
would be
wait.
0.
Yeah.
Yes, because,
It would just be throwing away the whole list.
So
okay,
somebody asks you what's the biggest number, you just write fold left, then put 1 dot dot.
Sure. Well, you need a function and an initial
The
state.
0 is the line.
But yeah, it's not the best. So to be honest, I look at type signatures all the time because things like this are confusing to everyone. I mean, you'll spend a lot of time looking up type signatures in Haskell and getting argument orders right because sometimes it's intuitive and sometimes it's not. I mean, this is something I've seen so much that it's natural to me, but I wasn't born knowing what fold L and fold R were.
It really starts to gel when you write more
And
static
then
type
give us-
coding. Like
It does.
it feels normal. If you just sit down and write some static type code for like a couple days, right? It's gonna feel normal, and you're gonna wonder like, why do I get to leave this out when you start writing?
And the good news is, when I fuck it up, the compiler tells me. I get a compilation error. So what do you guys think this is?
If we just, so I think it will be a curried function waiting for another argument.
Okay. We have
Uh,
curried function. I can tell you that that's not true. And if you
Damn!
if
I
you
thought I understood
Okay, I'm
that.
gonna go 0 on that.
That'd
Sounded so good.
That'd be 0, right? Doesn't really apply. to
Exactly.
function anyway.
exactly, it
If
doesn't
it's an empty list in Foldl, it like just
doesn't
takes
do any work.
the actual definition of Foldl.
Yeah.
You were foiled.
I'm still not sure I get it.
Like
It's-
Foldl is defined that like an empty list is like n or something.
Imagine empty rate dot inject 0 any block.
Oh, okay.
Explain it was
Oh,
really
yeah.
nice.
So the bad news in all this is that you can have thunk leaks. So here's Foldl as it's defined. And when you Foldl to some 1 to 10 to the 9, or 1 to 1 billion, you get Foldl plus 0 plus 1, 2 to the billion, or the list from 2 to a billion. And then you get Foldl plus this guy over here, nested 0 plus 1 thunk, inside a thunk adding that value to 2, and so on.
So lazy evaluation isn't free.
It can be not performant. Here's a complete example where we only have 3 elements. It builds up this nested thunk, and then once it's done, once it has the nested thunk, it starts evaluating it. And that can be a showstopper with a really big list. Where you
They
get
be smart enough to thunk their thunks. Like
Well-
to like
Think their thumb.
to like understand like what it's going to expand to and not think them before they're thunked.
So I tried this example. I even tried it at GHCI, and it actually didn't blow out memory. The compiler can optimize this kind of thing away, but you shouldn't depend on it. So I'm going to show you how to not blow up, how not to build up a nested thunk. And that's with Foldl prime, which is a non-leaky version of Foldl.
It's an Autobot.
And that is based on seek, which takes 2 values. It forces the first thunk, and it returns the second. So seek is a way to say, along the way to computing, seek x, y says, along the way to compute y, I want you to force x. So Foldl prime is very similar to Foldl, but when you do the F application, it forces it. So on the left we have the regular Foldl, which is building up the nested thunk. And on the right we have Foldl prime, which by using seek, that's what's in gold, it says, okay, FZX, I need to know what this is now, because I don't want to build up this nested thunk. I want to do this bit of work immediately. And you have constant space, because instead of building up a nested thunk, you have this number.
So is that available? Is Foldl prime like a?
It's in data.list. And the canonical fold actually is neither Foldl or Foldr. You'll use those sometimes, but the canonical fold is what's called foldmap, which I'll get to when we do monoids. And that has better performance for other reasons.
So if so you can use that with an infinite set, with 1 ... infinity.
No, you don't want to use it with an infinite set, because if you reduce an infinite set, you still have to do an infinite amount of work.
Okay, right.
Yeah.
Oh.
But there is a trick to that, which when I get into foldmap and why it's superior to Foldl and Foldr.
Oh, there's no like, you can't reduce it n number of times and then stop. Can you do that with fold?
That's a good question. I'm trying to.
I'm sure you could do it with your own. You just make your own, right?
Fold n L.
Or you could like fold
Fold n, fold L, and fold L.
You could fold
Fold
a
natural log.
Yeah.
you could fold a take.
Yeah, I see what you're saying. But
Fold a take. That's the
Fold a take. Thanks.
Yeah,
That's
you
what I
could
was
fold a
thinking.
take.
That's what I was thinking.
Yeah.
Now there is something interesting, which isn't.
That's not what I was thinking.
video. Basically, Haskell.
Yes.
It was a full L video.
So
That's the line.
what you can do, let's say that you have this guy, and you want to do a fold L of 4. So you want to see if there's some value in the infinite list that equals 1. And what am I doing wrong? Fold L. That's going to loop indefinitely, because it's going to do an infinite number of function calls. But there's this.
What about like quick? What about shortcutting, short circuiting?
It doesn't matter.
Oh, it doesn't matter.
But
Wait.
There's this concept called monoid.
This is before any evaluation, so it's like
Right, it's just
Tyler's
building up the function.
the expression
Right,
of
right,
value.
right.
There's this concept called monoid that allows you to, this is right. Do that instantly.
Can you fold L prime?
Yeah, can you go 2 up?
I'll do fold L prime, but it's not going to make a difference. You have to use foldmap for this particular
I have a
case.
question about
Why don't you fold foldmap for?
No, of course not.
Just
What-
give me the first.
But what's
they
your
do.
question?
Well, but I mean, you can't prove theorems that way.
Can?
You can't.
Why?
You can give an example. But
Yeah, but
it's-
it can iterate them.
That's equivalent to writing a C program that finds that.
What's your question? By the way, it's 7:02, so
I was gonna ask,
Oh,
how do you,
It is, indeed.
how does foldmap, oh gosh, know if there's like how does it know it's not present in an infinite list?
I'm going to go over foldmap in a later lecture.
Okay.
I just wanted to show that because
I
it's
was
cool.
curious.
It was the any. It was the any
It's because it's
monoid. that was doing it.
solved the halting problem.
Whoa, I didn't know Haskell was that good.
That's how good it is.
So as we wrap up, for technical note, you'll hear lazy and non-strict used interchangeably, but they're actually different. Lazy versus eager is about when the work is done, whereas non-strictness versus strictness is semantics. So lazy means I'm not going to do this work because I don't think I'm going to need it. Strictness may do the work, but if the value is never used, it won't cause an error.
So, kind of the point, I guess, of this like thunk of allowing like thunk bloat is that you can cause a memory leak, but it's at compile time, but it won't be.
No, it's at runtime.
Oh, is it runtime?
Yeah, it would be at runtime.
Okay. Oh, I see. Okay.
But the
Yeah,
advantage of it is that if those thunks are things that would, if you have an unneeded thunk
Yeah.
that blows up the world or that throws an error, it doesn't get evaluated. So often you'll see the upside down T, which is called bot, assigned to some kind of failure. So we just say equals bot to mean something fails. So 1 quad 0 throws an exception. Head of the empty list, pattern match failure. Something that doesn't terminate is also bot. Now when it comes to true and bot, that's bot. So you and true and a failing computation, you get a failing computation. But false and bot is false, because it never does that computation. So formally, a function is called strict in an argument if that argument's value being bot, that is evaluating that argue, triggers failure, causes the whole thing to fail. So plus is strict in both arguments, because to add 2 numbers, you have to know what they both are. But and is non-strict in the second argument. So what Haskell actually does is it evaluates thunks and it executes actions. And when the program runs, the action called main, which has the type signature IO of unit, is run. And the actions are then executed. And the thunks are evaluated as main requires. So this is the final exercise, and then we can all get out of here. Which bits of code do you guys think are going to run?
So is that all supposed to be run sequentially, as in?
Yeah.
So that's the whole program, right? You have the main.
Yeah, this is the whole program right here. We have the main.
Starts by running main,
Okay.
then it only evaluates what's needed for main to run.
Didn't see the.
So basically everything except for action 4.
Why is action 1 run?
Oh, sorry, I didn't see. Never mind. It's not me.
So action 2 is run, action 3 is run. Which variables are evaluated?
A, B, C, and B. Wait, sorry.
It's only A.
Just A and D.
And C.
Just A and
Well,
D.
but D.
D requires
is A and
C.
Open.
But D is
Yeah.
what? Oh, okay.
So
So
A
you
would
see
be
A. Nice.
Yeah, it's
Everything
a
would be.
it's a transitive closure problem. So first, action 2 runs, which says we need to return A times A. And actually, if we didn't print N, A would never actually be evaluated, because even though A is part of it, it's only the fact that main needs to know what N is, which is this A times A. And that A is 11, so it prints out 121.
So what would be evaluated if N is never printed?
Then it would perform this. It would perform this action.
Yeah. But it would never.
It would
evaluate
create a
it.
thunk, but it would never evaluate it.
But action 2 would get evaluated.
Yeah, unless the compiler was smart enough to optimize it out.
I see.
So, you know, the compiler might be smart enough to say, action 2 is doing work that doesn't get used anywhere, so I can toss it.
If it's type signature,
Well, wait a
you
minute.
include the IO.
It has IO.
It has IO, so it should
So
be
what should get run, right?
should be run. But if it didn't have IO, compiler could have.
Well, unless the compiler was smart enough to say, oh, this has an IO type signature, but it's a no-op, because it's never used.
Okay.
Yeah.
Oh, it can figure it out.
Maybe. I'm not sure.
Can we show that code that's never executed? Like, for example, we have the action 1 and action 4 never executed.
So, yeah, I mean, in this particular case, the dead code just isn't run.
Yeah, but can your static analysis tools
If you run, main, if you run main, all you afterwards. Right?
afterwards?
Yeah.
Can.
Because you have to execute it because
Yeah,
you don't
yeah.
know like has to be.
Well, I don't know if there's a tool that figures out where the dead code is, but there probably is.
There's gotta be, right? Because you have to foresee C++.
But can't you?
Even Java.
Can't you also? Can you do it statically?
Yeah, you could.
Oh,
It could be
exactly.
done
You
statically.
should be able to just look at the code.
And if your program takes like this, right?
Well, yeah, I mean, if it,
Well,
Like if you have a file name and everything what's in that file, like you call a function, you have to do over this.
Sounds like you're trying to introduce state.
don't do that.
Your state.
I'm saying if your main IO is really an IO rather than like there's communication and throwing it away.
sure. I mean, you have cases where you can say, okay, I don't know if this will be executed because it depends on user input, and then it's not dead code. If it can be executed for some state of the world, then it's not dead code, even if it's never
Exactly.
executed in a
In
particular
this particular
session.
run, yeah, but some
Yeah.
code is actually dead because it's never being called.
Right, exactly. So yeah, this is the live code, and the dead code fades away.
Having one request between them all.
All right, so do you guys have any
No, but
questions?
sometimes you can define a method that was never called.
Oh yeah, you're talking about from the static
Yeah,
evaluation.
yeah.
Right.
Could you go over what the fat arrow means again?
Sure. The fat arrow is,
Has photo.
please let me get this right. So
Fat photo, not fat photo.
Oh,
Oh, the fat arrow.
The fat-
It's problem.
It's
literally big bone.
Exactly.
Yeah.
the left on the fat arrow is the,
Thanks.
yep, of course, thank you. The left side of the fat arrow is the constraints on the types, because we have type variables in this plus. The reason for that is if we didn't have the constraint and the fat arrow, then we would say that we can plus for any type, and regardless of whether that's meaningful. So, for example, one of the first type classes that we get into is equality types, because there are types where you can't evaluate, you can't define equality.
Like function.
Exactly. Well, the problem with functions is that there is a definition of equality, but it's
Well, but
computationally intractable. Whether two functions are
no, but there's a
the
notion
same.
of identicality, right? Like you can see if the body is the same.
You could, but that would be misleading because
That part.
yeah,
I mean,
you'd have
in
false
in
negatives.
an object-oriented language, would just be like, are these objects identical? Is the memory
Sure.
being pointed at by these things the same? Right?
Yeah, physical equality.
But there's also is the body of the function and the formal's the same.
Yeah.
Yeah.
In this case, or we could just look at
So the constraints on the left side of the fat arrow tell you all the things that have to be satisfied for that to be a valid type. So if you have something like let foo x equal pair x plus 1, and actually there's a bunch of constraints on this bad boy. Show x. That has 3 constraints because based on the plus, it says, well, if we're plussing an x, then it has to be num. We're using compare, which means that it has to support comparison, so it's in the ORD type. I haven't covered that, so it's okay if you don't know what that is, but that's the type of things that have a meaningful comparison operator. And since we're also showing x elsewhere in the code, we have a show constraint on A.
Is this like very simple parsing exercise, or is it more like a Sudoku type of thing where you can backtrack depending on like what it encounters in the syntax tree of the function definition? Is it like do some sort of optimization to come up with like the most compact form, or because you can reason about stuff, right?
Sure.
About the relations between the type.
I don't think it always comes up with the most compact form, but it usually does. I mean, it's doing logical programming. It's you know, making inferences and combining them and unifying them.
Because this is basically like one of those like puzzles, right, where you know that like Sally is a firefighter and James live next to a firefighter.
Yeah. Exactly.
So they have to figure out what everyone is.
Exactly.
I'm a boss.
You have some weird stuff though that people
like Einstein was smoking a cigarette in the red house.
Yeah.
You have some weird stuff though that people have done with the type signature. So for example, there's I'm probably going to butcher this because this is like way beyond what we're going to do in the summer. Let's see if I have.
Is it list or list? What's a list? What?
Data kinds.
Let's see if I can get type level. Yeah. Okay. So you can do things like.
This is like the type system of the type system.
Yeah, but you can do things like data vector n nat a equals empty. You know, I'm not going to get this right right now, but you can annotate your types with natural numbers and have your vector type carry around the size of the vector, and then you can do things like have the type signature verify, for example, that you're not doing a dot product of vectors of different lengths. And when you start doing weird stuff in the type system,
You tried to complicate data frames.
Yeah.
But it's too complicated.
it can get complicated, yeah. And ultimately what we want from our type system is a simpler model of computation. So if you start putting arbitrary computation into your type signature, which you can do, there's a thing called dependent types that has essentially that effect. You can put arbitrary computation in your type system. Well, then you can have.
Then you get.
I was going to say you get undecidable type. You get undecidable compiles. That's actually a problem that Scala already has.
Right? Yeah. And it's like not like an implementation problem. It's like a theoretical problem. Right? Like you will always have that as long as the language definition stays this way.
Exactly. Exactly. It has undecidable type inference.
It's like not only is your language wrong.
Not only is your language wrong, but it was proven wrong 79 years ago.
It was a paper in 1972 that said, wait.
Good job there.
So Scala has that problem. Does Clojure have that problem?
Clojure doesn't have types, or it doesn't have static
Clojure
typing
is dynamically.
typed.
Right.
Yeah,
You can like type hint Clojure.
you can, but that's using Java-esque type hints, and Java actually has this thing called type erasure, which means that at runtime, information is lost. So when you have an array list, which is the Java list collection, the runtime does not know whether it's an array list of objects, meaning you can throw anything into it, or whether it's an array list of strings or an array list of. You can't put primitives in an array list, but you can put like the capital letter versions, like
Yeah,
the
yeah.
integer, the box types. So, but that all gets erased at runtime. It's generally considered to be a design mistake, but it is what it is. Because they didn't even have generics before 1.5. Any more questions? All right. I'm sorry? Well, but with data kinds set, you could do something like, I think you have to set GADTs. Let me see if I can get this. So then you could do like data vector.
Let me try this.
I have no idea if I'm going to be able to get this to work. T0A or econs. I don't know. I'd have to look
Not
into
even
this.
him.
No, I mean I know how to do it. I've done it before. I just don't know how to do it on the fly.
Sure.
So I'm not going to embarrass myself. I've already.
Can you whiteboard this for us?
There's like this Haskell model, right? Avoid success at all costs. And it's avoid dollar success at all costs, not avoid dot success at all
Exactly. Exactly. Yeah, people have been parsing that wrong for
costs.
a while.
You should have put the dollar.
It's like when someone says, I went to see a long ass movie, there are two parses of that that mean very
What was
different
the
things.
yes movie?
Exactly. All right, I'm going to turn off.
But yeah, asses are always left associated.
How do I?
Otherwise, you want like